So, hi everyone, and welcome to the sixth TIA Centre seminar of the academic year. So, my name's Adam Shepherd, and I'm a researcher here at the TIA Centre. And I'm also joined by Jachi online, who's now helping to co-host some of these seminars. And of course, it's an absolute pleasure to introduce Dr. Linda Studer today. Linda holds a PhD in computer science from the University of Freiburg, Switzerland, and has an academic background in life sciences. Her PhD mainly focused on the use of graph neural networks for colorectal cancer histopathology. Currently, she is a postdoctoral researcher within the computational pathology group at Radboud UMC, and she's working on the DIAGGRAFT project, which focuses on developing AI solutions for kidney transplant diagnostics. And as part of this project, she led the Monkey Challenge, which was at Middle in 2025 of this year, and has focused on the detection and classification of inflammatory cells in path-stained kidney transplant biopsies. She was also an organizer for COMPE at MICI 24 and MICI 25. And the title of Linda's talk is The DIAGGRAFT Project, Developing AI for Kidney Transplant Diagnostics. So Linda, thank you again for joining us. And with that, I'll pass over to you.
Thank you so much, Adam, and thank you for the invitation and the kind introduction. So yeah, I joined this project about a bit over 2 years ago, I think, as a postdoc. There have been other people working on this project as well. You'll see them featured throughout my talk. And yeah, I will give you kind of an overview of the different phases of the project, what we have been up to, and we are in the final stages right now. So how are we planning to how this is all going to be wrapped up in the end. But maybe let's start with some introduction on kidney transplant diagnostics. I know kidney is a bit of a niche topic. It's not cancer, it's transplant diagnostics. So what we're looking at is around a 2% increase in kidney transplantation rate over the last few years. And if we look specifically to the Netherlands, we can see that we have over 1,000 kidney transplant procedures every year, and also over 1,000 patients that remain on the waiting lists. So it's really important that every single transplantation counts, that the organs survive. And we actually see a 5-year transplant survival rate of about 80-90%, which means that these people will have to get a new donor organ if it doesn't survive. So the diagnostic is really all centered over the main priority to prevent the rejection, to keep the transplant organ as healthy for as long as possible, and maintain the transplant function. Now, the kidney is a structure that has two main parts. We have the outside area, the cortex, and inside we have what we call the medulla. This is made up of renal pyramids, these triangular shapes. And within these, we have the structures called nephrons, which is where the exchange between the blood and the urine happens for filtering the waste and removing excess liquids. So what this looks like in histopathology, so we have kind of the main feature is the glomerulus. That's always really easy to recognize on the tissue sections and these round structures. Then we also have the peritubular capillaries, or capillaries in general, which is where the blood is coming through. These are quite small, a bit harder to see. And then we also have the renal tubules, which is where the urine is flowing through. Now, in terms of diagnostics, diagnostics is done. So biopsies are taken as a checkup procedure to check the kidney transplant function, to see if there needs to be any adjustments in medication or a treatment plan. And the pathologists have a scoring system that's called the Banff Lesion Scoring system, where they have to assess 17 different factors, which then end up in 6 different categories for rejection. And these Banff Lesion score, they focus on the kidney structures, of course, like changes and inflammation within these structures. And then we also have certain items focus on active inflammation, for example. So no inflammation you can see here versus severe inflammation. And something chronic would be scarring, for example. So this is how it looks healthy. And then we have scarring, we have a degeneration of the tissue structures and a loss of functionality. And all these 17 lesion scores have 4 subcategories called no, mild, moderate, and severe. And looking at the active and chronic items, so When we have active inflammation going on, this is something that can be reversed with medication, the right treatment. But once we go into scarring, there's nothing you can do anymore, and you have a partial loss of function in the transplant organ. Now, the routine staining for kidney is a bit different. It's called the PAS staining. I think most of you will probably be familiar with H&E. It looks, in my opinion, fairly similar to H&E, but it does highlight some other structures that are important for kidney diagnostic a bit better than H&E. Now, just to give you an idea of how complex these 17 items are, I thought, I mean, don't worry, I'm not going to go into detail in this much, but just to give you an idea. So we really have these like 17 different items and the 4 subcategories. So you can imagine that this is quite a time-consuming thing to do, and it's very extensive. So this is where the idea of the DIAGGRAFT project comes from. Can we do this band classification with the support of AI to help pathologists be a bit more faster, be more, just screen and like look at all of these tissue sections and this extensive scoring system, right? So of course, we need to do tissue segmentation since we're looking at things happening in different tissue compartments. And this has, so this part of the project is done. Actually, the start of this was already done before the DIAGGRAFT project started. There was another PhD student working on a project that focused on tissue segmentation. Then the second step, as I said, inflammation is an important part. So we focused on inflammatory cell detection as well. This is where we collected a data set and invested a lot of time in making annotations, which then ended up becoming the monkey challenge that you've already mentioned in the introduction. So this, we started this last year in September, I believe, and concluded it in January this year. We're currently wrapping up the paper for that. So this step is also done. So what remains, what we've been working on in the last bit more half a year or so, is to apply the algorithms to a large study cohort that we collected and generate the AI outputs and set up what we call a reader study. So we want to validate the algorithm outputs by pathologists. We want to see how do they like to work with it? How does it help them to support in the diagnostic process? And we're currently running this. This is work in progress at the moment. Now, just to go back briefly to our table. So what we are addressing here is inflammation. These are the things highlighted in blue. And then the factors that we can now address with the segmentation project are highlighted, shaded in blue. So we cover, I would say, about half of the factors. Now, I'm going to delve a bit deeper into the tissue segmentation models that have been developed in this project or before this project. So first, Maike Hermsen was the PhD student that was working before the project. She collected a data set of over 17,000 annotations for 8 classes. I had a master student then last year to take her model and take her annotations to bring them up to the more state-of-the-art networks. So he ended up comparing 2 different networks, but what we ended up with is an NNU net, which is an automatic, like a UNet, but that does automatic network configuration. And we saw really nice results for him. So most of the classes we can really see have like a really high, nice DICE score. There's one class that still remains challenging, which is the atrophic tubules. So these are the tubules that are starting to get damaged and kind of die away. So the reason why this is a challenging class is that you can see, first of all, we don't have that many examples, and also because it's a gradual transition to atrophy. So, and there's not really a clear definition of when is the cutoff between normal and atrophic, since it's a continuous process. So it makes sense that the network is having a harder time with this. And they are sometimes also just misclassified as vessels or interstitium. That's the space in between. Another thing that we found is that tubules, which you can see here in pink, are kind of hard to separate because they can be very close together. And so ideally, if we want to do really automated classification, we would need to separate them so we can see the inflammation within. And he actually, to achieve this, he trained two networks, one for segmentation and then another one just for the border detection. And we found that this works really well to help with the separation. Now the algorithm, so the most recent publication on this was from the Compal workshop from this year. You can find it online, and you can also try the algorithm on Grand Challenge yourself. We've published it there, so you can upload your whole slides and you can run it on there and see how well it works on your slides. And if you have any questions, Sebastian is now a PhD student with us, so you can always, feel free to reach out to us. Now, what we're missing here with our A classes is one more important class, which is the peritubular capillaries. And these have not been included initially because they are small and they are really hard to annotate purely based on the PAS staining. So a separate project was initiated to work on the segmentation specifically here. And for this, we also needed a ground truth reference, which we used for immunohistochemistry staining for this, where you could really see, like now, like with specific markers, you can see nicely in brown highlighted the different tubules. And we used this to create a really strict hard ground truth for the segmentation. And we created, around 25,000 annotations, and for binary segmentation, so just the PTC segmentation specifically. And Mike and I did the initial work just using a standard unit, but then Lotte was our master student who took this further. And again, because we had such good results with the NN unit before, we again used the NN unit, and indeed were able to push the performance further. Now we achieved a DI score of 75% for the PTC segmentation. It still does remain quite a challenging task, especially in areas with scarring and inflammation, because when they get severely inflamed, they dilate. So we have a really high variety in sizes, which seems to be quite hard for the network to deal with. But generally, we can see that most of them get recognized the area more or less correctly. There are also like some smaller ones that are getting missed that are visible here in this dark red purple color. And then sometimes we also have some other structures that get recognized as a false positive. But overall, from the pathologist's perspective, being a very hard task, these were also very satisfactory results. Again, the most up-to-date version of this algorithm, the one that Lotte made, is also available on Grand Challenge. You can try it out yourself there as well, if you like. And the publication I've also listed here for you. That is just using the UNet, but exactly the same data set. Now, what we did is basically combine the outputs of these two networks. The NN unit also gives us kind of like a probability score for each class, which we then used to combine these two outputs to really have the complete segmentation that we are looking for within this project to give to the pathologists for the AI-assisted diagnostics. Now, that was step one. We're coming to step two, the inflammatory cell detection, the monkey challenge, which is open now again for submissions if people are still interested to work on it. The challenge phase, of course, is over. We ran that between September 2024 and January 25. Also presented the final results at middle 2025, which supported us. So that was great. But you will find everything and even more information here again on the website. Now, the challenge itself consists of two tasks. First, we have the overall inflammatory cell detection. And so this is what is used for diagnostics. They are currently not differentiating between different immune cells, but just looking at the overall inflammation. Now, we also wanted to add a second task that is computationally more challenging. And also we have some, there is some research that suggests that different inflammatory cells play a different role in the kidney transplant diagnostic. So we also, and since we were already annotating data anyways, we've decided to also add the task of monocyte and lymphocyte detection. So it's basically subcategorization of the immune cells in task 1. And the teams were free to either submit their solutions for task 1 or task 2, but actually all teams opted to submit solutions for both tasks, which was really nice to see. We had 2 different phases. So we had a model development phase with a live leaderboard where the teams over the span of 4 months or so could continuously submit their algorithms, and they could immediately see how well they were doing on the live leaderboard. And then based on that, they were allowed to select 2 models for the final submission to the test phase, which was then used to determine the winners of the challenge. And we also used holdout test sets from different centers data to do this. Then for the evaluation metric, for the leaderboard, we used the so-called free response operating characteristic. It is similar to a receiver operating curve, except that we plot the sensitivity versus the average false positives per square millimeter. And then we take the value at certain cutoff points. This has also been used in the Tiger challenge. Previously used for inflammatory cell detection scoring. Now we had awards for the top 3 teams for each of the tasks, and we were using grandchallenge.org to run this challenge, which some of you might be familiar with. Now the dataset creation for this challenge was very extensive and took quite some time, because we were again using immunohistochemistry restainings to create a very reliable reference. And for that, we collected slides from 6 different centers. They sent us their PAS slides. We, in our lab, destained them and restained them with quite a complicated protocol to make sure we really have the optimal visibility of the monocytes and the lymphocytes. So in red and in brown, you can see it here, but you can also see that there's quite a bit of background staining as well. So the staining optimization was really quite challenging. And for the PAS, we scanned them twice locally in the hospital with 2 different scan profiles. And for most of the centers, we also had the original scan available that they did at the center themselves. Now, we used AI to run an automatic detection, to train an automatic detection model. No, I think it was even just with the color decode, like just based on the colors, to do the detection on the immunohistochemistry, and then have a semi-automated annotation process, meaning that we had the automated detections, and then we could curate them. So delete the ones that were wrong and add the ones that were missing. So, and we had to register the 2 different scans as well, of course, so that we then in the end could transfer the data back to the PAS. This then ends, we end up with a very, very, very reliable data set, but it was a very extensive process. You can see here in red and yellow the annotations that we ended up with for monocytes and lymphocytes. And then, of course, this is the data set that went on to be used for the AI development. So the monkey data set, that's the data set that is the publicly available data set that you can still access on the open data registry from AWS, here with the QR code. We ended up with 81 whole slide images from the 4 centers, and we have 2 to 3 scans for the PAS stain, and then 1 scan from the immunohistochemistry stain that we also make available. Now, as already shown, we provide dot annotations of the lymphocytes and the monocytes, and also separately them combined as what I will refer to as inflammatory cells and in regions of interest. And of course, we also provide the region of interest masks, and then an Excel file with some general information about the rejection category and some information about the immunohistochemistry's staining quality and the registration quality, in case people are interested in this type of paired data. Now, I thought maybe some of you are interested what goes into running a challenge on Grand Challenge, actually. So I've added this slide here as well. So Grand Challenge is a platform that provides you with a secure environment to run and evaluate the algorithms really completely closed off. So there's no data leakage you have to worry about. You can really set up your test set and your validation set completely on the back end securely. So from the participant side, what they will have to do is to create a Docker image that they then can submit to the Grand Challenge website. And this is then, so a Docker container. So this is then taken by Grand Challenge, will run on the back end, is applied to the data set that has been uploaded. And in our case, that would be one of the whole slide images and then the region of interest. And then on the back end, it generates the output, which are 3 files. So lymphocytes file, a monocytes file, and an inflammatory cell file. And this is then sent to another Docker container that does the evaluation. And the evaluation is then sent back as an entry to the leaderboard, which will, if you set it to live, you can also set it that it doesn't directly go live, but it's kept back first. And the contestants can then see their entry on their leaderboard. They can see, they can also open up a visualizer to see the actual output that was produced. And in our case, we also provided them with some additional output files so that they could plot the FROC curves themselves just to look at them, because Grand Challenge at this point doesn't support images being directly uploaded to the leaderboards. Yeah, so this is kind of the workflow that you will have to set up, that you will be working with if you ever want to run a challenge yourself. Now, we had, thankfully, I had really no idea what to expect and how many people would actually participate in such a thing. But when I checked last Friday, we had a total of 570 people who requested access to the challenge. By now, you can also see it's like globally very spread all over the world. And during the challenge phase, we had 135 submissions to the live leaderboard phase. So that doesn't mean 135 teams, like many teams obviously submitted multiple times continuously to improve their algorithms. Yeah, and in the end, we had 7 teams that submitted to the final test phase. So the teams that were allowed to submit to the final test phase were the ones that had a successful submission to the live leaderboard phase. Now, I know that this is not a surprise to the TIA Center, but in the task 1, the inflammatory cell detection, the team from the TIA Center, so TIA Kong, which was led by Jackie, won that challenge, followed by InstantSec and iNflammatory. You can see that this was a PhD student from the University of Edinburgh, and iNflammatory is a company from India that was participating. And you can see actually, yeah, they were, especially the top 2 were fairly close together in terms of scores, but overall also, I think the top teams had kind of like, yeah, achieved very, very similar scores. So it was really cool to see, to have different approaches like work really well. And for the monocyte and lymphocyte detection task, we had we had similar ranking. In this case, the InstantSec team slightly took the win, and we averaged the performance per cell type. Actually, ST Medical would have been 3rd if we looked at it individually. They also had a really good working algorithm for the monocyte detection specifically. Yeah, now we've been evaluating the results a bit further, of course, since then, also for the publication. Just to give you a bit of a visual impression here as well. This is the ground truth, and then we have the outputs of the top 3 teams here. You can see it's, I would say, fairly similar, but what we do see is that TIA Kong has a bit less false positives, which is really nice. And actually, but the monocyte detection is really something that we find really remains challenging, but this is also not surprising based on the feedback that we got from pathologists. So whenever I presented this project in front of pathologists, they were like, are you sure you can do this with the distinction of the monocytes and the lymphocytes? Because for them, it's really, really challenging to do that in PAS. So they were all kind of excited, but also a bit skeptical if this was going to work. And this is also kind of what we found, that it's possible, but it's still work in progress. And yeah, looking at it, also together with Dominique, who's a pathologist, we quickly realized that like for a visual aid, it's much more important to have not as many false positives, because our brains are better at just kind of like adding in the missing cells rather than subtracting the ones that are like wrongly popped up. So this was also nice to see that actually the winning solution from TIAGGRAFT was the one that had the least false positives. And we even optimized the detection threshold based on what was found visually acceptable by the pathologist, and which was a precision of over 70% and a recall of at least 60%. And we saw that TIAGGRAFT's algorithm actually achieved that in over half, in more than almost 60% of the test cases that we had, which was really nice. So we were really happy with that, and we are currently using it now also for the reader study. And we were really happy to have an output that was really usable to move forward to the next step. And we were also very glad to see that there were no systematic misclassification patterns. So there were no like types of cells or types of structures that consistently got misclassified. It was always kind of the case that the pathologist was able to find a reason why it could have happened, like saying like, oh yeah, this looks a bit like this, or this is another type of inflammatory cell, and the nucleus looks a bit more like this type of cell. So that was also reassuring to see. Next I'm going to just give like a very, very short breakdown of the different algorithms. They have everything public on their GitHubs, in their papers, so please feel free to go read the papers. I will not be able to answer questions in much detail on that, unfortunately. So yeah, TIAGGRAFT, I mean, Chucky is here, so if you have questions to him, I'm sure you can ask at the end. They used a multitask encoder-decoder architecture, and they had 3 task-specific decoders, one each for the different tasks, so inflammatory cells, lymphocytes, and monocytes. And they also used nucleus detection as their main tasks, but also 2 auxiliary tasks to further even improve the network. And their paper is out as a preprint with even further evaluation, more extensive benchmarking, called CONGNET. So do go look it up if you're interested. Then InstantSec was actually the only team or the only person who used the immunohistochemistry data that we made available, which was also really exciting to see. So Thibaut first trained a detection model that detected the monocytes and lymphocytes on the IHC, and he created and then applied it to larger areas. So he created what he calls a silver standard data set, which with pseudo-labeled data, which he was then able to transfer to the PAS since all of the slides were registered. So I think he also made this data set publicly available. So obviously it's not curated, but he had really good, he really achieved really good performance on the IHC. So I think the silver standard data set is also pretty reliable. And then he went on to train, to use a 2-step approach. First, nucleus segmentation using the InstantSec network, and then in a second step, the nucleus classification as monocyte, lymphocytes, and other using EfficientNet. So basically, any nucleus that was detected but did not align with the annotations got classified as other. And then, he just pooled the monocytes and lymphocytes together for the inflammatory cell output. You can find quite extensive documentation on his approach also on his GitHub. Now, the third place went to iRA-Matrix. This team used an ensemble of 2 models for each task, kind of pretty straightforward detection models. For the lymphocytes detection, they used dyno data approach, and for the monocyte detection, they used YOLO V5, and they also pooled the outputs together to get the inflammatory cell detection output. So yeah, that was that for the monkey challenge. As I already briefly mentioned, we're currently bringing it all together. So we have now the segmentation algorithms. We now have a well-performing inflammatory cell detection algorithm. And now we would like to know, is this even useful for the pathologist? And this is the work that we have in progress. We just finished the first round of the diagnostic validation study. And no, actually, we just started the second round. Sorry, we finished the first round. Now we had a bit of a wait time, and now they go back and do it again. So we can also compare a bit how they do with and without the AI. And so we collected a cohort of over 300 patients. And we have, in the end, now we have 40 pathologists that completed the first set. We've divided them into smaller groups so that we can cover more cases, and we can compare also how they do like within each other. And the main questions of interest that we have is the inter-observer variability of the individual Banff scores. So it's quite already established in literature that some of these scores suffer from high inter-observer variability. So we would like to see if we also observe that, since we let them really score like the full set. And also the impact of AI on the inter-observer variability, to see if they're like more coming together to like a similar agreement. Then we also have some questions in there about the usefulness of the AI outputs, like how do they like to work with them? Do they find it helpful? Do they use it as a first look, as a second look? Do they use it to find, I don't know, like certain specific areas for specific factors? I think the third point will be the hardest to assess, and I'm not sure if we're really covering. I think we wanted to cover it, but I think we will only kind of scratch the surface on that, like the influence of AI assistants, because we will let them first, some of them are scoring first with AI and then without AI, and vice versa. So we can see how they look at the same case with and without AI. So that will give us a little bit of an idea how the AI influences their decision making. But of course, this is a very complex question, and because we don't restrict them to how they use the AI, so they're allowed to use it however they like. I think we will also have like kind of a limited, it will be more of a mixed bag of impressions rather than a very controlled study at this point. This is really kind of a first pilot in that sense. And to give you an idea what this looks like, so we have, again, we're running this on Grand Challenge, and here it's quite small to read, but they have all the different the Banff scores that they can go through as a multiple choice. Here's the scroll bar, so it's like a whole range of questions. In the end, they have some free-form questions about how they use the AI, did they like the outputs, with any feedback they would like to give us. And then they have the normal PAS stain that they can look at. They can also maximize both of these as like a full screen. Then we have side by side the AI output. Also, when they move around, like both of these move at the same time. And they can also, for each individual AI output here, they can like toggle it on and off. So if they just want to look at just at the inflammatory cells, they can toggle off anything else that they want. They can also, start. I think we let them have everything going in. So when they come here, everything is turned on in that sense, and then they can go from there. But they can really choose if they want to just see one specific structure or if they want to see everything. I realized I was a bit quicker than I thought. I hope that's not a problem. But there's obviously many people involved in this project. I think most foremost, I would like to mention Dominique van Midden. She is the PhD student whose main focus was this project. So this project is really her PhD project. And it's been amazing to really have a pathologist on this project. I think this is what's made this really successful. We had really like a diverse team from Jeroen van der Laak, who's the professor in digital pathology, then Luc Hilbrands, who is a clinician, and then we have two pathologists, Erik Steenbergen and Jesper Kers, who also works extensively in computational pathology. And then we had a whole bunch of people supporting the project, master students, AI engineers, medical students, of course, all of our collaborators at the different institutions that helped us collect the data. the Banff Digital Working Group that supported us, and all the readers that we have now in the reader study, and last but not least, of course, the participants of the Monkey Challenge, because without them, we wouldn't have any of our nice algorithms that we have right now. So yeah, I'm really happy to take any questions. Hope it's okay that we fell a bit shorter.
No, of course. Thank you very much. It's been a brilliant tour. So yeah, let's open the floor to questions. Does anyone online or in person have any questions? I can see one already. I think Ruby Wood has asked on the chat. Great talk, thank you. And your last slide of the AI viewer for pathologists, there was some leak of classifications at the boundary with the green class into the white space. Do you have any ideas of how to deal with this on the AI side? And do the pathologists have any comment on this as well?
Do you mean here? Probably right. Yeah. So the border is always a bit of a challenge because generally what we do is kind of like a two-step approach where we first have a network that segments the tissue areas on the slide. And then so that we can focus the approach. So we can focus the application of the algorithm just on the detected tissue. This, of course, is usually has like some margin of error here that you can see that bleeds a little bit out here, especially also if we have like fatty tissue on the slide, that sometimes creates some issues. To be honest, I am not super sure how to deal with this. I think it often then either thinks, oh, it's like something that's connected, like here, like an adjacent structure, or it's other type of structures that have a lot of like white space. I think if we would have a tighter tissue segmentation, we could definitely alleviate that. But in my experience, the pathologists don't mind too much visually, but of course it's a problem when you then want to do some automated assessment, because if you have suddenly like a much larger area for one class that you're evaluating on, then that's not what you want, right? It does. I think also we see it sometimes because it's not on here now, but we also have the class empty glomerulus, which is literally an empty glomerulus. So you have really like white space like that, and that needs to be like correctly detected as such, right? And then sometimes you have like large like dilated vessels that also have a lot of white space in it, and it really depends. I would like if there was somebody working in the future on the tissue segmentation. I think a multi-resolution approach could be really nice, because I think some structures are really easy to recognize at large magnification, and for some you really need to zoom in. I think maybe that like zooming in and out could help a little bit.
Sure, thank you. And I don't know if I missed this, but it seemed from looking at the top performers that there weren't any foundation models being used in this segmentation, which is quite refreshing, I suppose. Do you think that's as a basis of using these sort of path stained slides as opposed to H&E? Do you think that's the main reason why they weren't used?
I think there were teams, but I don't remember on the top of my head, that used some pre-trained backbones that they then fine-tuned. So actually, if I go back to the tissue segmentation, here, so in this paper, Sebastian also tried to use SAMpath. So that's like an adaptation of SAM that came out for Compile 24. That is supposed to help, like, be specific for pathology. And he did find like it got similar-ish results, but always a little bit like subpar, especially also in the borders, like in kind of the delineate, like really isolating the different structures. So if you're interested in that, you can have a look. But we hypothesized that it is because I think maybe Virkov, the new version now includes PAS, but I think as far as I'm aware, none of the other ones actually use PAS stained data. So it's kind of our hypothesis why maybe it's not working so well, or we just didn't try the right model for this specific task. I think, But I know there were one or two teams that did use some foundation models in the inflammatory cell detection.
Sure, thank you. I think there's a few questions on the chat still as well. So I think Jachi's asked, he said, thank you, Linda. which Banff scores benefit the most from automated inflammatory cell quantification? And do you plan to automate any of the remaining components of the Banff scoring system?
Right. So here you can see the full list of 17, and the ones highlighted in blue are the ones that relate to inflammation. And so for these here, we are looking at the number of inflammatory cells within a certain substructure, which is why the substructure isolation is really important. But I think the clustering of the cells really gives them like a nice view to go look for the most inflamed structures, which is what they have to do generally. So yeah, this is like in the interstitium, in the glomerulus, in the tubules, in the vessels, and also in the capillaries. And then total inflammation, as far as I'm aware, but Dominic will be the right person to answer this question. It's just overall inflammation in general. And then we also have like inflammation in certain specific areas that are called IFTA, which is where we have fibrosis and tubular atrophy. Yeah. So what we're also working for now so we're not really looking at automating any of the other things, except maybe having a combined segmentation model and not these two separate ones. We're rather more looking at really seeing how it could work in diagnostics. But what we also want to do, and we're working on definitely for the readers, the paper on the reader study, is to have an automatically computed Banff score. So we are working on getting like the individual objects and being able to count the number of lymphocyte, the number of inflammatory cells within them, so that we can have a comparison. I think we will not be, we'll have to, so we can see, does it make sense to emulate the Banff criteria, which in my opinion is probably more challenging, but I think rather can we see what correlates best. So maybe the average number, the maximum number of, let's say, inflammatory cells within a glomerulus correlates well with the glomerulitis score, for example. This is definitely something we want to investigate. We're working on this right now, and hopefully, we will definitely include that in the final paper on the reader study evaluation, how exactly this correlates, basically. Yeah.
Sure. Thank you very much, Linda. And there was a few more questions as well on the chat online. I know Chachi's asked another question. Rose has made a comment as well about the segmentations, but has also asked, does your data set include GFR of patients?
This is a very pathological question. I hope she's here by now. She would know, because I unfortunately don't. I'm sorry. It doesn't seem like she's here yet. Would you like to send me an email? Then I can answer that question for you.
No, thank you.
And I will forward it to our pathologist who,
Okay. And I think Jackie's had another question as well. Did the monkey challenge reveal anything unexpected about what types of models perform well?
Yeah, I think for me, the unexpected thing was maybe how many different models, wait, where are they here? Seem to, like, you can choose different approaches and still end up in a similar place.
Yeah.
I think we saw some trends, like efficient net was one that was very commonly used. I think a few people used YOLO, which is not very surprising then because this is a detection task. I think some people used a two-step approach. Many people used ensembles. But overall, I didn't expect to have such a, I think, broad diversity of different approaches, or sort of all end up in a very kind of similar ballpark, right? Especially I would say the top four.
Brilliant. And I suppose aside from the actual, in terms of the actual challenge, obviously you guys over at Radboud now have done lots and lots of different challenges. So what would you say is the most challenging part of organising some of these challenges?
The challenge of the challenges.
Exactly.
So let me think about that. I mean, obviously collecting the data set was in our case time consuming and challenging, but I think that was very specific to the type of task that we chose. Then kind of making sure the data is all correct and right on Grand Challenge and your evaluations are correct. I think there it really is worth it to invest a lot of time into like doing good quality control, making sure this is all running smoothly. We had some hiccups there, but I think most of it you can really smooth out and address if you're really responsive. So I tried like with the team to really reply to everybody in the forum within less than 48 hours. Basically, I wanted to keep everybody who was working on it motivated. I wanted to show them that like we're here if there are questions, we're here to help. We'll try to troubleshoot, to really get as much community engagement as possible. I think you never really know what's gonna happen, but I think if you're well prepared in terms of data quality control, and you allow yourself enough time also to smooth out some hiccups. I think that was really nice with the middle. Like we didn't have a strict deadline for the end of the challenge like you have with like the Mikai challenges, for example. So we had a hiccup over Christmas, but we could just say, okay, everybody, you have 3 more weeks. Like we just add 3 more weeks at the end, I think it's really that. Be generous with the time that you allow yourself to get everything ready and then set it up. And the Grand Challenge team is also was very supportive. So all in all, I really enjoyed that experience. It was for me the first time doing this, but it was really nice to just talk to all these different research groups and see everybody getting involved, honestly.
Oh, fantastic. Okay then. So does anyone else in here have any more questions? Or any more questions online? Nope, I don't think so. We've got a question from Jack.
Well, I honestly, I keep losing track. So I think there will probably be a few more upcoming. I know today they were talking about, I think out of the unicorn challengers, I think are still open and running. So there's a lot of tasks. So you can really have like a full playground there. And I think they were also talking this morning about more maybe more like benchmarking for like foundation models and things like that. So I'm sure there will be more challenges coming out of Radboud. We're looking forward to your participation from the team.
Oh, excellent then. Okay then. Well, I think with that we'll draw the seminar to a close. But thanks again, Linda, for a really fantastic talk and for taking the time to speak to us.
Thank you so much.
Thank you. And just a reminder for everyone else, for everyone, we haven't got any more seminars booked this side of Christmas, so we've got a bit of a break now until the new year. And our next seminar will be on Monday, the 19th of January, with a talk by Dr. Diana Felizardo from IMP Diagnostics in Portugal, where she will discuss her work on Do Androids Dream of Digital Diagnoses? So a pathologist's perspective on digital and computational pathology. So hope to see you all there. But for now, thanks again, Linda, and thank you everyone online and in person.
Thank you, Adam.
Thank you.